In this lecture, we shall be starting our discussion on something called TCP/IP protocol stack. So, the title of the lecture is TCP/IP protocol stack, the first part. Now, in this lecture, I shall be talking about firstly the TCP/IP protocol stack on which the internet is basically based on. We shall be looking at the basic functions of these TCP, UDP and IP, the most important three components of this TCP/IP stack, and with the help of an example we shall see the concept of something called data encapsulation. So, let us start with TCP/IP, what it is actually. Now, as I mentioned, TCP/IP is the most fundamental protocol in the internet. Just to imagine what is an internet? Internet is a network of networks. There are so many networks, they are all connected together. Inside a network, there are so many different protocols that are being followed. Computers are connected to it, but somehow they are all able to communicate with each other. So, there must be some common language all these computers are speaking, and it is this TCP/IP that is the common language. So, if a node you connect to the computer, if it understands this TCP/IP protocol, then it can communicate with the internet to any other computer in the world, right. Okay. Now, TCP/IP, by virtue of its standardization, this allows computers to communicate and share resources over the internet all across the world. This is used as an universal standard, okay, in the internet. Now, this TCP/IP as a universal standard is used to bridge the gap between various different platforms. Well, when you say platforms, you can think about operating systems to start with. You have Windows, you have Linux, you have Mac, then you can have different kind of networks also. You have Ethernet, you can have ATM, you can have so many other kinds of networks. Talking about wide array networks, there are also so many standards are there. So, there are various alternatives and options available at every step. So, how do you make them work together? It is this TCP/IP. TCP/IP is the common glue that binds everything together, right. Now, this TCP/IP, the work or the standardization started in the early 1970s as part of a project which was initially funded by the US military, but subsequently it spread to the different universities and finally it became a de facto standard in the internet. Okay. Nowadays, everybody uses TCP/IP. Now, in TCP/IP, the network layering, well, you have already seen in the previous lecture the 7-layer OSI model, which was proposed by International Standards Organization. Now, for TCP/IP, there is a similar kind of layering which is followed, but it is somewhat simplified. It does not contain all the 7 layers. In fact, it uses a very much simplified 4-layer model. There are only 4 layers here. Okay. So, in contrast to the 7-layer OSI model, TCP/IP has only 4 layers. Let us try to see these layering side by side and try to make a comparison. Okay. Here you see the 7-layer model on the left and the 4-layer TCP/IP model on the right. In the 7-layer model, as I mentioned, the lower 3 layers are the point to point layers and the upper 4 layers are host to host layers. Now, in the TCP/IP, what they have done, they have simplified that the all upper 4 host to host layers, they have integrated in a single application layer. Okay. You see, it depends on the application whether you actually require a session, whether you actually need to do some changes in your data presentation. So, it really depends. So, instead of keeping separate layers, the TCP/IP has integrated all of them in a single layer and calling it the application layer. And this transport layer, this of course has a more or less correspondence with the transport layer here. This is a host to host layer. This is responsible for end to end message transfer. Network layer also has a correspondence. Network layer is mainly responsible for packet routing, delivery of packet across the internet, across the network. And again this data link and the physical layers, they are merged together and they are referred to as a single link. Sometimes this is referred to as a data link or a physical link, they are called differently. The point is that in a computer system, when you want to connect it to a network, there is some kind of a network card you want to use, network interface card, and the network interface card typically integrates both data link and the physical layers together. That is why in a simplified TCP/IP model, the two layers have been merged into a single layer. Okay. So, this is the simplified 4-layer version in TCP/IP. Now, in this 4-layer model, when you think of the data transmission, again it is somewhat simplified, as you can see here. This A is the sender, C is the receiver and B is an intermediate node. So, this A generates some data from some application, from application it goes down to the transport layer, from transport layer it goes down to the network layer to the data link layer, and to the data link layer it sends the data actually over the data link or the point to point link. Now, this intermediate node B receives the frame here, sends it up to the network layer takes a decision where to forward the packet next, and accordingly it sends it down to the data link layer of the outgoing link. This B may be having several outgoing links. There will be one data link corresponding to every outgoing link. So, it will be sending out to the data link corresponding to the correct outgoing link, and the frame will be going there, received, and it will be traversing the reverse direction and finally to some application in the destination C. Now, you can see this transport is an end to end layer or host to host layer, as if A and C are communicating directly. This intermediate node B is not visualized at this layer and also at the application layer. Okay. These are called end to end or host to host layers. Now, talking about the TCP/IP protocol suite. TCP/IP protocol suite is not a single protocol, but rather it is a family of protocols, a collection of protocols. That is why it is called a family of protocols, and these protocols are all based on datagram mode of data communication. They do not rely on virtual circuits, they rely on datagrams. So, all these things we have already discussed earlier. Datagrams are sent independently from one node to another to as a sequence of datagrams, they are all independent, okay? And the same message can be broken up into several packets, and each of these packets or datagrams may follow different routes. So, may follow different routes. So, delay may be variable, the arrival order at destination may be different. This already we have discussed earlier. Okay? All right. Now, this is a diagram which shows some of the TCP/IP family members. There are more in fact. So, the most important ones are shown here. So, in the lowest level, this is the data link layer. Sometimes it is called the data link and hardware layer, as I said, physical layer, different names. So, if you have an Ethernet connection, you will be using an Ethernet layer here. This will be an Ethernet network card that will constitute the lowest layer. this is your network layer, this is here you have the network layer. Now at the network layer, the most important protocol is the internet protocol or IP. IP is the most important protocol that is responsible for routing of the packets, right. Now, in addition there are some other protocols, I will briefly talk about this after this, ICMP, IGMP, ARP, RARP, I will talk about this. They all work at the network layer level. At the higher layer, transport layer, there are two alternate protocols, TCP and UDP, transmission control protocol and user datagram protocol. And at the topmost layer, application layer, you can have any arbitrary user applications running. Now, in addition, as part of the TCP IP, there are some specific applications also which are also included in the family, like file transfer protocol, trivial file transfer protocol, simple mail transfer protocol. All our email is sent and received using this SMTP protocol, simple network management protocol, domain name system, and so on. There are many others. Okay. So, this is just a very quick picture. Now, talking about these four, I will very briefly talk about these. This address resolution protocol or ARP, this is basically used to convert the IP address. Well, each computer is having an IP address, will have an IP address. This IP address is converted to an hardware address which is called a MAC address. MAC address is referred to as a hardware address. The reverse address resolution protocol or RARP does the reverse. It converts the MAC address or hardware address to IP address. Now, whenever data are flowing in a network in a LAN, these ARP and RARP protocols are very useful. They are used quite widely. We will be discussing this later again. Now, then we have this ICMP or Internet Control Message Protocol, which is mostly used for a device on the network to send error message to other members in the network, okay? Like some service not available, something not found, etc. And finally, Internet Group Management Protocol IGMP. So, here a node can communicate with its adjacent routers some information about its multicast group membership. Like whenever it wants to do some broadcast or multicast, selectively it wants to send data to some set of nodes. So, it can inform the routers that this is the kind of multicast groups that you want to send data or receive data from. So, these protocols are roughly used for these purposes. Now, a typical scenario I am showing here, well, here I am showing two paths, one is a TCP path and other I am showing a UDP path. Well, here the application will be some user process which will be using TCP at the transport layer level, TCP will be using IP at the network layer level, and IP will be using the lowest layer hardware layer level. Or you can use UDP, the user process may be communicating with UDP, IP, then hardware layer level. So, what I mean to say is that when you are developing some application, you may either choose to use TCP or you may choose to use this UDP. Both options are available to you. TCP has some features, UDP has some features. Depending on your suitability, what exactly you need, you can use either TCP or UDP. But the point to note is that below TCP and UDP, you have a common member IP. So, IP is the network layer, it is a basic datagram routing service, okay? That is common, but above IP you have a choice, you can have either TCP or UDP. Now, very briefly let us look at the functionality. Well, what does IP do? Well, IP is responsible for routing of the packets or the datagrams. It transports datagrams or the packets from a source to a destination. This is called routing. So, it will decide which node to forward the packet next. That next node will again decide where to forward that packet next. This way the packet will finally reach the destination. So, the network layer or the IP layer in each of these nodes will be responsible for this routing or packet forwarding. This IP has an additional responsibility. Well, if it finds that a packet is large, too large, it may break a packet into smaller packets. This is called fragmentation. This we shall see. The point to note is that IP uses datagrams, and we mentioned earlier when you talked about datagrams is that datagram is an unreliable service. Unreliable in the sense that some datagrams might get lost, some duplicates might get generated, datagrams may be received out of order at the destination. So, such scenarios may happen. So means if you are using IP, you must be aware of these problems, that some packet may actually get lost. Okay? Fine. TCP understands that IP that is there below is not reliable. TCP tries to make the network connection reliable by taking some additional responsibility. How? TCP will explicitly check whether the data that is being sent is being correctly sent to the final destination, because the destination will be sending back an acknowledgement. So, the sender will know whether it was received correctly or not. If it sees that it was not received correctly, then the data will be transmitted again, so that some kind of reliability is maintained. So, essentially TCP tries to provide a connection oriented reliable service. Reliable service in this context, if some packet gets lost, it will get retransmitted. Connection oriented in the sense that the application running on the receiving end will have an illusion that, well, as if I have some kind of a connection oriented connection, some kind of a virtual circuit or some kind of circuit switching is going on. Data is coming and the data is being received in the same order. But as I said, IP does not guarantee that. IP may receive the packets out of order. So, now it will be the responsibility of the TCP layer to order the packets in the correct order and then forward it to the application. So, that the application will feel that, well, everything is fine, the packets are coming in the same order, but it is TCP which is ensuring that. Okay. So, TCP will be splitting a message into packets, reassembling the packets at destination, and if some packets were lost, as I said, it will be resending. So, all these services are done by TCP. And for actual data transmission, it interfaces with IP in the way that each packet it sends it to IP for delivery, and IP will be using its own rules and its own routing tables to transmit and receive the packets. And if there are some errors happening, well, IP will not handle any errors, it will be handled by TCP. TCP will check that whether all the packets are arriving correctly or not, and if some packets are missing, it will be requesting the sender to send it again. Okay? Something like this is happening. Now, UDP is a simpler version of TCP, which is basically quite similar to what IP is, just a little thing extra is there beyond IP. You see, UDP does not provide any kind of reliable connection. So, what UDP says is that it provides a connectionless, just like a datagram, unreliable, just like a datagram, for sending datagram. That means, you can say UDP and IP are very similar. It just provides a transport layer interface to directly interface with IP. It does not provide any reliability like TCP. It does not order the packets like what is done by TCP. It simply receives the packet as it comes. There are some applications where even if some packets get lost, you do not care. Like periodically, some network equipments are sending some status information to a central server that, well, I am good, or what is the status. Well, even if 1 or 2 packets get lost in between, it does not matter, because anyway the next packet will be coming again very soon. So, I will know about the status. So, there are some applications where reliability of communication is not important, and we can use UDP, because UDP is much simpler to use. The packet format is simpler and it is also faster. We shall see later that how the packet formats look like, right. So, UDP is simpler, because it is simpler, that is why it is faster. You see, as I told you, with each data some headers get added up. For UDP the header is small, for TCP the header is much bigger. That is one way you can understand why it is faster. Okay. And it does not care about error control. If there is an error, let it be. Some packets are lost, fine. So, it does not care about it, all right, fine. Okay. Now, the point to note is that in this TCP IP, this simplified these 3 layers, there are several addresses which are coming into play. At the lowest layer, hardware layer, well, most commonly we see something called Ethernet networks, that is there at the physical layer level in our local area networks. So, at the lowest layer, this is the most common kind of network we encounter. It is called Ethernet. Yeah, this is the Ethernet. Now, in this Ethernet, there is a concept of Ethernet address, which is 48-bit address. The Ethernet cards which you plug in your computer, which is plug in your laptop, they all have an Ethernet interface and they have a 48-bit so called MAC address or Ethernet address. That is unique. Each such Ethernet card in the world that is manufactured, that has a unique 48-bit address. At the network layer level, at the IP, you talk about something called IP address or Internet Protocol address, that is a 32-bit address that identifies a supposedly unique address of a network interface. Whenever you connect a computer to a network, that network interface will be having an IP address associated with it, and that IP address also is supposed to be unique, but that is a 32-bit address. And at the transport layer level, you see there are so many applications or user processes which are using the network. How to distinguish that which user process is sending data, which user process is supposed to receive data? There is a concept of a port number or a port address. Port address actually uniquely identifies a particular application or a user process running on a machine. So, whenever a process sends a data packet, the corresponding port number is carried with the packet, and whenever you say a packet comes back, it is received, there is a destination port number. That destination port number will tell you where to forward that packet. There may be many applications or user programs, which program to forward it to. So, this port address basically uniquely identifies one of the user processes or user programs running on a machine. IP address identifies uniquely the network interface, and physical address, as I said, this is a characteristic of the network interface card, and every network interface card has a unique network address. Well, there is a concept called encapsulation. Let me briefly talk about it with the help of an example. You see, you have seen the network protocol stack. So, in the network protocol stack, data flows in one direction, and the receiving end, it will flow in the reverse direction. Now, as data flows down, some headers and sometimes some trailers are added to a packet, and on the other side, as the data moves up, these headers are getting removed or stripped out progressively. Okay. So, here I will take an example of a very simple application, TFTP. TFTP is a file transfer application, it stands for Trivial File Transfer Protocol. So, as an example, I am assuming that there is a TFTP client, a program which is trying to send 200 bytes of data to a TFTP server. Okay. Now, for TFTP protocol, the header is 4 bytes, that is defined. Okay. So, with this assumption, let us see. This is the data which you want to send. This is 200 bytes. This is 200 bytes. So, when it goes to the TFTP application, so TFTP application appends a header. This is a header of TFTP which is 4 bytes. This is the data which TFTP application generates. It sends it down to the transport layer, to UDP. TFTP uses UDP, does not use TCP. Okay? That is why it comes to UDP layer. Now, UDP header is 8 bytes, this we shall see later. So, at the UDP layer, an 8 bit of header gets added. Then it comes to the IP layer. For IP layer, 20 bytes of header gets added, and at the lowest level, it is the Ethernet. At the Ethernet layer, 14 bytes of header and 4 bytes of trailer gets added. A header gets added here, a trailer gets added here. So, ultimately in the network, in the LAN, whatever data gets transmitted, it is this whole data. You see how many bytes? 14 plus 20 plus 8 plus 4 plus 200 plus 4. So many bytes of data will finally get transmitted, but ultimately I was trying to transmit only 200 bytes. So, the remaining things are overhead, networking overhead. This is something you need to remember. So, as I said, as we move down from the application down to the lowest layer, these headers slowly get added, but at the receiving end, when you receive this whole thing, so it will again be sent up to the application, and here the reverse thing will happen. Step by step, these headers and trailers will get removed. In the next step, this will get removed, next step this will get removed, next step this will get removed, and finally, we get our 200 bytes of data, right. This is how the thing works. So, with this we come to the end of this lecture. So, here we had talked about some aspects of the TCP/IP protocol. We shall be continuing with our discussion on TCP/IP protocol in our next lecture as well. Thank you.